Okay, so in this lecture, I'm going to be following up what we learned last time about how there are fundamental definitions of temperature, pressure, and chemical potential related to changes in entropy with respect to energy, volume, and number of particles. And today we're going to be talking about those quantities in the context of different types of equilibrium. So for the most part in this course so far, we've been talking about thermal equilibrium, where, for example, two Einstein solids may be exchanging energy between them until they reach an equilibrium where the energy is divided up equally if the two Einstein solids are the same size. But in today's lecture, we're going to talk about two other types of equilibrium in addition to thermal equilibrium, and that is mechanical equilibrium and diffusive equilibrium. Okay, so we're going to start off by sort of making a table to summarize these different types of equilibrium. So maybe we can put a title up here. Different types of equilibrium. Okay, so I'm going to make a table where the leftmost column of the table is going to specify exactly this: what type of equilibrium are we talking about? And then as we go to the right, the first thing I'm going to specify is what type of quantity is exchanged between the two systems as the system goes to equilibrium. Okay, so first, the case that you're more familiar with. So if we're talking about thermal equilibrium, then the exchanged quantity as it goes to thermal equilibrium, the exchanged quantity is energy. And more specifically, we usually mean heat. There's some heat exchange between two systems. Energy is exchanged until the two systems reach thermal equilibrium. And okay, so let me also point out that okay, so we can talk about the quantity that's exchanged. Another thing we can talk about for each type of equilibrium is what is the quantity that is equalized in the two systems when they reach equilibrium. So in the case of thermal equilibrium, the quantity that is equalized is the temperature. So let's write this down. The quantity that is equalized at equilibrium. So for thermal equilibrium, that quantity is temperature. And in this fourth column here, I'm going to write down what is a sort of fundamental definition of the quantity that's equalized. So fundamental definition of this. Okay, so in this case, as I talked about in the last lecture and previously in the course, temperature can be defined as ds du minus 1, holding fixed number of particles in the volume. Okay. And then finally, in the last column here, I'm going to draw a picture of a simple example here. So, and the example is in the case of an ideal gas again, or two ideal gas systems, really. So in this case, you could draw a picture of a box that is thermally insulated from the outside world, but it's divided into two sections, And one side we could say we have gas A, on the other side we have gas B, and there is some exchange of heat. There's heat gained or heat lost by the system until they reach thermal equilibrium. So this dividing wall here is a thermal conductor. It's thermally conducting, allowing heat to transfer between the two gases. I guess this outside material is insulating. And in this picture then, the point is that as if you started out in a situation where the gas A was hotter than gas B, then energy would be transferred to gas B until they reach the same temperature, right? So T A equals T B at equilibrium. All right. Let's go on to the next case here. So the next case is mechanical equilibrium. So let me draw the picture first here to help you understand exactly what I'm talking about. All right, so imagine again you have a box divided into two halves with gas A on one side, gas B on the other side, and separating the two gases you have a flexible wall. So you could imagine some kind of rubber membrane, for instance, that is allowed to flex and change its shape such that these two systems will reach a mechanical equilibrium. And okay, so first note that this is a flexible wall. So you should think of this as something like a balloon where the balloon, for instance, has a gas on the inside and the room has gas on the outside. The balloon reaches a size that's constant when it reaches a mechanical equilibrium with the room. So when gas A reaches mechanical equilibrium with gas B, the pressure on either side of the wall is fixed. That's what decides when this wall stops moving. Okay, so pressure A equals pressure B at equilibrium. So the way you can think about this is that the exchanged quantity here, what's the quantity exchanged between A and B? It's volume, right? If this wall bends to the right, in some ways you can think of it as gas B is giving up volume to gas A. Right? So volume is exchanged, and the quantity that reaches the same value for gas A and gas B is pressure. And as we introduced in the last lecture, pressure can be written as temperature times ds dV, holding fixed the energy and the number of particles. Okay, so the last case that I want to write is diffusive equilibrium. So in diffusion, the reason diffusion happens is that two systems are not in diffusive equilibrium. So diffusion happens by exchanging particles. So if you have particles that are exchanged between two systems, in order to reach diffusive equilibrium, the quantity that is equalized when the two systems reach diffusive equilibrium is the chemical potential that we introduced in the last lecture. And we also defined chemical potential in the last lecture as minus T times ds dn, the number of particles, holding fixed volume and energy. Okay, so what kind of picture should you have in mind here? This should be, again, you have a box that has a gas A on one side, a gas B on the other side. And now you should imagine a wall that has some holes in it. So these holes, I don't know if you can, hopefully I'll make my holes bigger so you can see them on this camera that I'm recording with here. So there's holes in this wall that allow particles to pass between the left side and the right side of the box. So it's kind of, in fact, there are gas molecules of type A and B on both sides of the box. And at diffusive equilibrium, the two things that are equalized, like we said, are chemical potential. And if you remember from the last lecture, that chemical potential is closely related to the concentration of particles. So what's going to happen here is that at equilibrium, the number of particles of type A on the left side will equal the number of particles of type A on the right side at equilibrium. And the same is true for the gas particles of type B. You could write Na, or you could write Nb left equals Nb right at diffusive equilibrium. So this wall has holes in it, allowing particles to pass from one side to the other. Okay, so I'm going to write one last bit of intuition or intuitive information on this chart. That is, one way to think about temperature, pressure, and chemical potential is in a qualitative way the following. So you can think of temperature, if you're going to ask the question, what is temperature? And we have a fundamental definition here, but maybe a more intuitive way to think about it is you could think of it as the system's, how willing it is to give up energy or heat, right? So if one system is at high temperature, it gives up heat to the other system. So this temperature you could think of as willingness to give up heat. Okay, now, so that seems fairly intuitive. How about for pressure? Pressure is, it's different. So it's not the willingness to give up volume. You might say that initially, following the logic of this diagram, but it's actually the opposite. That is, if something is at high pressure, then it wants to expand, which is in a way its willingness to take volume from its surroundings, right? So gas A, as it pushes to the right here, is taking away volume from gas B and taking it for itself. So this is more like the willingness to take volume from its surroundings. Now, chemical potential is, see, it's got a minus sign here, so it's not the willingness to take, it's the willingness to give. It's going to be the willingness to give up particles, right? If you have a high concentration of type A particles on this side compared to that side, then this side will be at high chemical potential compared to that side. So the high chemical potential side is the side that has a strong willingness to give up particles. So let's write that down. Okay. And that completes this table. Now I'm going to erase this, and what we're going to do next is a little bit more of a mathematical view of equilibrium and trying to relate it back to what we've learned earlier, that is that equilibrium, the process of going to equilibrium, can be thought about as it's just the system trying to reach the most likely macro state available to it, right? So in other words, trying to reach the state with an extreme value of entropy, a peak maximum in entropy. Okay, so that's what we're going to do next. I'm going to erase this table. Okay, so just to start with, let's work on the simplest example first. So example 1 is for thermal equilibrium. And this is in some ways just a recapitulation of something I've shown earlier in other lectures, but I just want to show these things in parallel so that it's clear how they're related. So at thermal equilibrium, like we said before in that table, the two things that are equalized are the temperature of system A and the temperature of system B. They become equal at thermal equilibrium. So what I'm going to set out to do now is to prove that, given the fundamental definition of temperature, that this statement implies that you reach an extreme value of entropy, okay, for the system as a whole. Okay, so let me just put a little aside over here. So what we're thinking about here is that the macro state of the combined system that is system A and system B together is, in this case, the temperature of system A and the temperature of system B. So the macro state is this combination of TA and TB. If you know TA and TB, then that you have specified the macro state of the system. Not the microstate, the macro state. Okay, so if you want to know, what we're going to try to show then is that when TA is equal to TB, that is the macro state with the highest multiplicity, which entails the highest entropy of the total system. Okay, so what we want to show is that S total equal to, which is, this is the sum of the two entropies of the separate systems. We want to show that this is maximized. So this is our goal anyway. Our goal is to show that this is maximized when the two temperatures are equal. Okay. So let's start with this as an assumption, and we're going to show that the implication is that S total is maximized. Okay, so to start with then, let's rewrite this in terms of the fundamental definitions of temperature. So this guy is, if these two things are equal, then these two derivatives are also equal. Remember that I flipped them. I flipped these two things again. It used to be a -1 power here, but if TA is equal to TB, then 1 over TA is also equal to 1 over TB, so these two derivatives must be equal. Okay, so if this is a true statement, and we know that the system, well, if it's a closed system, so that is an assumption here, thermal equilibrium between two bodies that are interacting with each other, but otherwise it's closed off from the external world, that means that you can think about some total energy that's just the sum of these two things, and it's constant. So this is a constant. Therefore, if you consider a small change here, this is 0. There's no change in the total energy, but this is true then, that DUA plus DUB is equal to 0, which means DUA equals minus DUB. Okay, and also we know that the total, well, this definition of the total entropy here, so DS total equals, so this definition here implies that DS total equals DSA plus DSB, so some small change in the total entropy. And keep in mind, total entropy is not a fixed quantity. It's not a conserved quantity like energy. Energy is constant because it's thermally isolated, but that does not imply that the total entropy is fixed. In fact, as you go from different combinations of TA and TB, this is exactly what we're saying, that some particular combination of TA and B will maximize S total. So S total is changing as you change TA and TB. Okay. So let's then rewrite this statement. So we're continuing here. So this says that dSA dUA equals dSB dUA with a minus sign here. I've used this relationship to replace the dUB here with a minus dUA. Okay? And I'm going to do a little fast moving that to the other side of the equation here. So the sum of these two quantities must add up to 0. And you can now see that this is in fact ds total dUA, right? You had a dSA plus dSB. That's a ds total in the numerator divided by dUA. So this is equal to 0, right? So this says then that if the temperatures are equal to each other, then the entropy is at a peak with respect to some transfer of energy between system A and system B. We could have also equally shown that ds total dUB is equal to 0. Both of those are at an extreme value, a peak, when the system is at equilibrium, that is TA equals TB. So this implies that we're at an extreme value of S total. And we're not going to prove it here, but it's straightforward to show, for particularly for the ideal gas, that this extreme value is a maximum and not a minimum, for instance. But we're not going to show it right now. Okay, so next I'm going to have a similar argument. So example 2, a similar argument for mechanical equilibrium. So in this case, the macro state is not going to be talking about the temperature, but this is the situation where we're talking about some system that has a flexible barrier between it that moves until the pressure on either side of the barrier is equal. That's the mechanical equilibrium example. So this is example 2. We're talking about mechanical equilibrium. In that case, the macro state of the system is the pressure of either side. Actually, it's the pressure and the volume, I guess. VA, because both of these things can change. The macro state of the system is a particular combination of volumes and pressures. But the goal is the same, almost here. The goal is the same. It is to show that when pressure A is equal to pressure B, then the entropy of the total system is maximized. That's what it means in terms of the statistical mechanics view. That's what it means to be at equilibrium. So that's what we're going to try to show, is that if PA equals PB, then S total is at an extreme value. Okay, so same strategy, roughly. That is, we start with this statement, which should be true at mechanical equilibrium, and see what that implies in terms of the fundamental definition of pressures. Right, that's PA, so that thing has to be equal to the pressure of system B is equal to TB DSB dVB. Okay, so this is our condition that the pressures are equal to each other. Okay, so, and note that in this particular example, mechanical equilibrium, I don't actually specify what the temperatures are. In fact, we don't care what the temperatures are. In order to reach mechanical equilibrium, this flexible wall between the two systems adjusts itself, adjusts the volumes until the pressures are equal. But it doesn't say anything about temperature. So one way to think about this is that the flexible wall, in fact, is not allowed to exchange heat, for instance, that the two sides could be at any temperature. Okay, so in order for this statement to be true for any two temperatures, TA and TB, the only way for that to be true, it turns out, is that if this derivative and this derivative are both independently equal to 0. But let's write that down in words here and think about it a little bit. So if, let's see, let's put it this way. For this to be true for any value of TA and any value of TB, the only way for that to be true, if you know, come up with any kind of values of TA and TB you can think of, and if this situation has to be true for any values of TA and TB, then this thing has to be equal to 0 and this thing has to be equal to 0 independently. That is, we must have the dSA dVA equals 0 and dSB dVB equals 0. Okay, so if that's true, then it's a few more steps then we can use to prove that ds total is in fact extreme. So let's see, yeah, it's fairly straightforward. If we replace, for instance, here, we use this to say that dSA then is equal to ds total minus dSB. Then we can replace, so let's just take this one and plug that in. So we get ds total dVA minus dSB dVA equals 0. And we know that, again, okay, so the volumes are, in a sense, just like the energy in the last problem, the volumes are conserved. That is, we're thinking about a box with a flexible wall between two sides, but the total volume of the two parts of the box remains the same. So the total volume is fixed. So if V total is the sum of the two sides, then we can replace this dVA with this. This implies that dVA equals minus dVB. So this is straightforward. We can say that ds total dVA minus or plus dsB dVB. So I've replaced the dVA with a minus dVB here, equals 0. And we also know that this has to be 0, right? We just said that this has to be 0 from the beginning. So that says then that, again, then that the total entropy is at an extreme value. So that means then that so ds total, or S total, is at an extreme value at this condition where PA is equal to PB. Okay, so we proved it. Again, this is proving, what we're doing here is just proving what is already intuitive. The table that I put up at the beginning of this was an intuition, giving you intuition about these different types of equilibrium, and here I'm proving that they correspond, these intuitive ideas correspond exactly to maximizing entropy, or maximizing, finding the macro state with the highest multiplicity, the highest entropy. That's what we're talking about. So let's do this one more time for the chemical potential, which is very similar to the argument I just did for the pressure in mechanical equilibrium. So this example is diffusive equilibrium. And here the goal is to talk about some changes in NA and NB, or I guess, yeah, so this would be the number of type A particles on the left side. Maybe we should write this differently, but okay, so remember that we want to say that the chemical potential on either side is equal at the diffusive equilibrium. And we want to use this to prove that S total reaches a maximum, just like in the previous arguments. So this one is quite similar to the last argument. So first thing we do is replace this with the fundamental definitions of chemical potential. Okay, so that's just replacing mu A with the definition of mu A minus TA times ds dna. Okay, so now we just need to show again that this equation implies that S total is maximized, and the argument is very similar to the last one. That is, this statement must be true for any combination of TA and TB. And we're not talking about temperature here, we're just talking about diffusion of molecules. So for any combination of TA and TB, this statement is only true if this guy must be equal to 0 and this guy must be equal to 0 for all values of TA and TB to make this equation hold. Okay, so and just like the last argument, in fact, the last argument we had was V total is equal to VA plus VB. The same is true here. We can say that the total number of particles is a conserved quantity. It's the sum, oops. This is the number of particles on one side of the barrier. The number on the other side has to add up to some total number that's not changing. And likewise, the total entropy is related to dSA and dSB by these equations. So you should see at this point that the math is exactly the same as the last case, and that this fact together with these facts together with this requirement that this is 0 and this is 0 has to imply that, again, ds total, so I'm skipping all the math here. You can look at the volume argument from the last case to see how this works. This quantity is also maximized, or the derivative is 0, meaning that S total is extreme, is at an extreme value. So again, I'm not proving that it's a maximum, but you have to take my word for it for now, because I'm not going to prove that in this lecture. But it is. S total reaches a maximum at the particular combination of Na and Nb that result in equalized chemical potentials. That's the point here. Okay, so that's it for this lecture.